In this lesson you will learn how to find critical points. A point is called a critical point if the point x is in the domain of the function and it is the point where the derivative is equal to 0 or where the derivative does not exist. So there are different types of critical points. The two relative extrema are the relative maximum and the relative minimum. And the third type is a terrace point. So all of the points I'm labeling all have horizontal tangents, which means that at all of these points the derivative is equal to 0. Points A, C, and E are all relative maximums, and points B, D, and F are relative minimums. F is a relative minimum, but it doesn't have a horizontal tangent. The derivative does not exist at this point. The terrace point is neither a maximum or a minimum, but the derivative is still equal to 0, so that is point G. For number 1, the directions are to find the critical numbers of f of x. Anytime you're asked to find the critical numbers, you take the derivative and set it equal to 0, and if there is a restriction on the domain, you take the restriction and set it equal to 0. For number 1, the directions are for each function find the critical numbers of f of x. Anytime you're asked to find the critical numbers, you take the derivative and set it equal to 0. If there is a restriction in the domain in the derivative, you have to also find that value. But for part A, when I find f prime of x, we get 6x squared plus 6x minus 12. And to find the critical numbers, we take 6x squared plus 6x minus 12 and set it equal to 0. To solve for x, I have to factor, but I see that everything is divisible by 6. So if I divide each term by 6, I have x squared plus x minus 2 equals 0. And this factors to x plus 2, x minus 1. So that x is equal to negative 2 and x is equal to positive 1. And I can see by the graph that I have a maximum here and a minimum here. So this is the point 1. This is the point negative 2. And to find their corresponding y values, I find f of negative 2 by taking negative 2 and substituting it into the original function. So I have 2 times negative 8 plus 3 times 4 plus 24 so that I have negative 4 plus 24, which is equal to 20. So this critical point has coordinates of negative 2, 20. The next critical point is we take f of 1 and we substitute 1 into the original function. so that we have 2 plus 3 minus 12, which is equal to negative 7. So 1, negative 7 is also a critical point. And we can see by the graph that negative 220 is a relative maximum and 1, negative 7 is a relative minimum. For part B, f of x equals x squared minus 4 to the 2/3 power. So to find the critical numbers, I find f prime of x, which is 2/3 times x squared minus 4 to the negative 1/3, because I subtract 1 from 2/3, but then I have to multiply this by the derivative of what's inside using the chain rule, and I get 2x, so that I can write the derivative as 4x over 3 times the cube root of x squared minus 4. So in this question, there are two types of critical numbers. One is when the derivative is equal to 0, and the other is when the derivative does not exist. The derivative is equal to 0 when the numerator is equal to 0. So I take 4x, set it equal to 0, and solve for x. So x is equal to 0. And to find the y-coordinate that corresponds to x equals 0, I find f of 0 in the original function, so that I get negative 4 raised to the 2/3, which is the cube root of 16. I square the negative 4, and the cube root of 16 can be written as 2 times the cube root of 2, because 8 times 2 is 16. 8 is a perfect cubed, and it comes out as a 2. So that the critical point where the derivative is equal to 0 has coordinates 0, 2 times the cube root of 2. So if I look at the graph on the right, I can see that this point here is the point where the derivative is equal to 0 because it has a horizontal tangent, and its coordinate is 0, 2 times the cube root of 2. The next type of critical point is when the derivative does not exist. The derivative does not exist when the denominator is equal to 0. So if I take 3 times the cube root of x squared minus 4 and set it equal to 0 and solve for x, I start by dividing both sides by 3. And to solve for x, since it's under the square root, I would square both sides so that x squared minus 4 equals 0. And I continue solving for x. X squared is equal to 4, and when I square root both sides, x is equal to plus or minus 2. Now I can see from the graph that 2 and negative 2 is where the cusp is located, and at a cusp the derivative does not exist. So it makes sense that these points were found by setting the denominator of the derivative equal to 0. And to confirm that their y-coordinates are both 0, I find f of negative 2 by substituting negative 2 into the original function, so that I have 4 minus 4 is 0, to the 2/3, which is just 0. So -2, 0 is a critical point, and when I substitute 2, I will also get 0. So the three critical points are -2, 0, 0, comma 2 times the cube root of 2, which we found earlier, and then +2, 0. So the three critical points are -2, 0, 0, comma 2 times the cube root of 2, and +2, 0. For part C, f of x equals x plus 1 over x. So once again, I start by taking the derivative. F prime of x is equal to For part C, f of x equals x plus 1 over x. Before I take the derivative, I want to write f of x as x plus x to the -1. And I do this so that I don't have to use the quotient rule for 1 over x. So that when I find f prime of x, the derivative of x is just 1, and then minus 1 times x to the -2. So I can write the derivative as 1 minus 1 over x squared. But when you set the derivative equal to 0, you must write this as one fraction. So I find a common denominator of x squared, and I write this as x squared minus 1 over x squared. So the derivative is equal to x squared minus 1 over x squared. Since I have a fraction, there are two types of critical numbers. One is when the derivative is equal to 0, and the other is when the derivative does not exist. The derivative is equal to 0 when the numerator is equal to 0. So x squared minus 1 equals 0. And when I square root both sides, x is equal to plus or minus 1. And to find the y-coordinates that correspond to plus or minus 1, and to find the y-coordinates that correspond to plus or minus 1, I substitute -1 into the original function, and I get -2. So the point -1, -2 is a critical number. And to find the y-coordinate that corresponds with 1, I get 2. So the other critical number is 1, 2. So on the graph, this is the point -1, -2, and this is the point and this is the point 1, 2. The next type of critical number is the one where the derivative does not exist, and this is found by setting the denominator equal to 0. But when I set the denominator equal to 0, I get x equals 0, but to be a critical number, the value must be in the original function's domain. If I look back at the original function, f of x equals x plus 1 over x, 0 would make this function undefined, and looking at the graph we can see that we have an asymptote at 0, so therefore x equals 0 is not a critical number, because it is not in the original function's domain. So therefore the only critical numbers are -1, -2, and 1, 2. We can see by looking at the graph that -1, -2 is a relative maximum and 1, 2 is a relative minimum. For part D, f of x equals 12 times x to the 2/3 minus 4x. So I will start by finding f prime of x. So 12 times 2/3 x to the -1/3 minus 4, and if I rewrite this derivative, I have 8 over the cube root of x minus 4, but when you find the critical points, you must have this as one fraction. So I find a common denominator, which is the cube root of x. So I multiply both parts of the second fraction by the cube root of x. So the derivative is equal to 8 minus 4 times the cube root of x over the cube root of x. So I have two types of critical numbers, one where the derivative is equal to 0, and the other when the derivative does not exist. So the derivative is equal to 0 when the numerator is equal to 0. So I take 8 minus 4 times the cube root of x equals 0, and I solve for x. And I get the cube root of x is equal to 2. And to solve for x, I want to cube both sides so that I get x is equal to 8. And to find the y-coordinate that corresponds, I take 8 and I substitute it into the original function, which is 12x to the 2/3 minus 4x. So I take 12 times 8 to the 2/3 minus 4 times 8. 8 to the 2/3 means the cube root of 8, which is 2, squared is 4. So I have 48 minus 32, which is equal to 16. So this critical point has coordinates 8, 16. And we can see by the graph that this point, 8, 16, is a point where the derivative is equal to 0 because it has a horizontal tangent. We also know that it's a relative maximum. The point where the derivative does not exist, we can see by the graph, is going to be where the cusp occurs because cusps are not differentiable at the point. So the point where the derivative does not exist, we find that by setting the denominator of the derivative equal to 0. So we take the cube root of x, set it equal to 0, and to solve for x we raise both sides to the third power so that we get x is equal to 0. And to find its corresponding y value we substitute it into the original function. So that we get 0 minus 0 is equal to 0. So the second critical number, or critical point, is the origin. And looking at the graph, that's where we expected our point to be because the derivative does not exist at a cusp.